Hey everyone, continuing our discussion on the preliminaries, in this video we will discuss the Lagrange dual of an optimization problem. In optimization theory, duality is the idea that optimization problems can often be viewed from two very different perspectives. As with all things optimization, duality theory also originated from linear programming. The story goes that George Danzig, who was an expert in optimization, and he once presented the idea of linear programming to John von Neumann, who then conjectured the idea of a corresponding dual problem by relating it to two-person games. In the modern context, there are several duality theories such as Lagrange duality, Fenchel duality, Wolf duality, etc. Of these, Lagrange duality is by far the most useful. However, we'll take a look at Fenchel duality also in the next section as it relates to conjugate functions. In general, optimization problem that we start with is called primal problem, and we use it to construct the corresponding dual problem. The overall approach has three steps: associate Lagrange multipliers or dual variables with the constraints, write down the Lagrangian, which is given by objective plus the Lagrange multiplier times the constraint functions, and finally minimize the Lagrangian with respect to the primal variable in order to obtain the dual objective function. And that allows us to write down the dual problem. To streamline the notation, we define the so-called standard form of an optimization problem. It is written as P is equal to minim over x in calligraphic x, f of x, subject to inequality constraints of the form gi of x less than equal to 0 for I equal to 1 to m, and equality constraints of the form hj equal to 0 for j is equal to 1 to p. In this problem, the set calligraphic x is a subset of the domain of the problem, which is the intersection of domains of f, domains of gi's, and domains of hj's. A remark is that we use this notation to denote the subset. Some of you may have seen this notation as well, but for our purposes, both of these notations mean the same thing. That is, x could be inside or equal to d. Note that the requirement that x should belong to the intersection of domains of all the functions is always implicitly present in every optimization problem. Most of the times, however, the domain restrictions are not stated explicitly, but in all scenarios, you must remember that implicit constraints are actually present. Finally, the functions f, gi's, and hj's are all extended real valued proper closed functions. When encountering a generic optimization problem, there are several possibilities. The typical case is that the problem is solvable and p turns out to be a real number. It is also possible that the constraints are such that there is no x that can possibly satisfy them. So that problem is infeasible. Finally, it is also possible that while the constraints are feasible, the objective function is unbounded below for some feasible x. Since we have been considering the extended real line, we can let p take infinite values for these two atypical cases. By convention, we let p to be infinite when the problem is infeasible and minus infinity when the objective is unbounded below. Next, we look at the definition of the dual problem formulation. We begin with associating dual variables with all the constraints. Specifically, we are associating lambda I with the ith inequality constraint gi of x less than equal to 0 for I from 1 to m, and we are associating nu j with the jth inequality constraint hj of x equal to 0 for j from 1 to p. We will collect the dual variables into an m cross 1 vector lambda and p cross 1 vector nu. The Lagrangian is a function of x, lambda, and nu, and is given by f of x plus sum over I equal to 1 to m, lambda I gi of x plus sum over j from 1 to p, nu j hj of x. The domain of the Lagrangian is calligraphic x cross rm plus cross rp. That is, the Lagrangian is only defined for x belonging to calligraphic x and a non-negative lambda. The dual function is an extended real valued function of the dual variables and is given by q of lambda comma nu equal to min over x in calligraphic x, L of x lambda nu. A key property of the dual function is that it is concave. To see this, recall that we saw in the earlier video that the pointwise maximum of closed convex functions is also convex. The same result stated differently is that the pointwise minimum of closed concave functions is also concave. Here it is easy to see that the Lagrangian is an affine function of lambda and nu. Since the dual is pointwise minimum, it is therefore concave. Recall also that we defined that the function to be proper if it was never minus infinity. Similarly, we defined domain of a function to be set of all x such that the function was less than infinity. However, those definitions were for functions that are to be minimized. Here, however, we are dealing with q which has to be maximized. So equivalently, minus q has to be minimized. So the requirement for q to be proper is now that it should be less than infinity. And likewise, the domain of q is defined as the set of all lambda comma nu such that q is greater than minus infinity. Finally, we write down the dual problem, which entails maximizing the dual function subject to lambda greater than or equal to 0, as well as implicit constraints that lambda and nu lie in the domain of q. Depending on the structure of the problem, the domain constraint could be complicated. Remark that in the same way as p, the value of d is also allowed to be infinite. But the convention is opposite here. That is, if the dual problem is infeasible, we assign d equal to minus infinity. Then d can be finite, of course. And finally, if the dual problem is unbounded above, we assign d equal to infinity. A final remark that dual problem is formulation dependent. If the primal problem is changed in any way, the dual problem would look different. So that's it for this video. In the next video, we will see weak duality theorem, which is basically an implication of the way in which dual problem is defined.